Each year, more than 3 million people from around the world visit Yellowstone. They come to see the most famous geyser in the world.
There are hundreds, thousands of wonders here, really world-class wonders.
It's been 2 centuries since that first Euro-American walked through this awe-inspiring land. 70 of those 200 years were used exploring and establishing it as a national park. The remaining years have been spent trying to balance nature with park visitors. It's a process that's still being learned.
It's pretty good today, but in my opinion, it needs to be even better.
To their mostly illiterate counterparts of the early 1800s, the stories were beyond the scope of imagination. The tales were routinely filed in the category of fictional entertainment. John Coulter was the first of these Euro-Americans to bring back reports of the thermal areas. His listeners thought they were hearing the ravings of a deranged man. They laughed and scoffed at his descriptions, labeling the area Coulter's Hell. Our narrative begins with Coulter's discovery, the first of many, which led to the preservation of the wonderland we now call Yellowstone. The story starts near present-day Bismarck, North Dakota. The year was 1806. Lewis and Clark were returning from their exploration of the Oregon country. He recounted to a skeptical audience the facts of his adventure. He told of waterspouts,
as Coulter's Hell.
The gold strikes in Idaho and Montana brought a population base close to the region. They established towns and cities.
During the 1860s, gold strikes were made in Montana Territory, notably at Alder Gulch and up by Missoula.
Several mining groups shoveled and panned their way through Yellowstone, looking for that elusive end of the rainbow. We do know he traveled along the western shores of Yellowstone Lake and then followed along the Yellowstone River. He was probably the first Euro-American to also see scenes like these. was the season of short days and cold, long nights. They visited the lower geyser basin once again, where the year before he had witnessed and recorded 2 geysers. Daisy and the Grand.
Soon after reaching camp, a tremendous rumbling was heard, shaking the ground in every direction. And soon a column of steam burst forth from a crater near the edge of the east side of the river. Following the steam arose by a succession of impulses a column of water apparently 6 feet in diameter to a height of 200 feet, while the steam ascended 1,000 feet or more. We called this the Grand Geyser, for its power seemed greater than any other of which we obtained any knowledge in the valley.
Dr. Hayden's party, along with
That was made by folks who came on a horse with a pack string. They were mounted.
In 1877 was important in another aspect of Yellowstone's history. With the Army came the manpower and authority to
The Army had no use for him, and they just tossed him out in his ear. He didn't have his permits, and they dismissed him.
and under its control the park hotels, transportation, and visitation rights were established.
Spectacular. It is an old center cone. That center cone is deposits of geyserite, which is the silica that's dissolved inside the hot thermal waters. That silica becomes deposited on top of these cones. That geyserite grows about 1 inch per 100 years. So you can imagine, just if you guys will let my other people through, just come on in and get a little cozy, because it's going to get cozy up here. Everybody's going to come in and want to see this. So it kind of gives us an idea how old this particular cone is. I'm not going to go into too many other things about what I want. want you to look at right now is what's erupting. It's called the beehives indicator. This is not a predictable geyser, but as we talked about, as we started to come up here, there's lots of mysteries and there's lots of clues that we can unravel to give us an idea of what these things are doing, when they're going to erupt, and beehive is a classic example of that. The indicator goes off for about anywhere from 20 to 34 minutes before an eruption on an average. Right now, the indicator eruption is approximately 22 to 24 minutes. What's going to happen is it's releasing the pressure, and you know how that pressure starts to build. And we haven't talked about the characteristics of geysers yet, but we're going to talk about that. We're doing a little impromptu. We're going to move our stuff around so we can see this go into eruption. As we know, Old Faithful goes into eruption about 130 to 150. This is a true fountain geyser. It shoots straight up in the air like a nozzle spray. The pressure is so great because there's constrictions. And keep in mind, this thing's going to go about 180 feet on an average. Sometimes it can reach up to 200 feet. So it's really spectacular. Here we go. There we go. Enjoy this. It's truly rare. I'm going to get out of your way. Now there. Eruption is about 5 minutes. Old Faithful's anywhere between half an hour and a half. Of course, you've got an Old Faithful eruption now. How spectacular. Listen to the sound, people. Listen to that sound. That's just ginormous power. Yeah. The question is the water hot? No, by the time it comes back to it goes 100 feet here. And by the time it comes back down 100 feet, water. Go ahead. It's really kind of fun. Replicate nature.
Double rainbow? Double rainbow Panama. You have other kind of juice in water.
That's all nature. It's all nature. Isn't that amazing? So this was approximately how many hours? 14 hours in between. This is better from Old Faithful, but it seems like this is stronger coming up. Yeah, it's like the pressure's greater. The spout, the Dyke spray is better. It's more direct. Because if you ever get a chance to really look at Old Faithful center cone, it's not as compact as this one is. The constriction is a little bit larger at Old Faithful.
What's all this white mineralization on the ground?
Hey, how are you doing? It's always looking up. It's always, yeah, it is, isn't it? It's always good to see this. Blue Star is right on the other side of the Firehole River. You see where people are standing, kind of gathering? So was that worth it?
Yes, that was
I'm telling you, it's fantastic to see that going to Eruption. There's truly one of my favorite geysers is going to Eruption.
You might have mentioned this, but how often does this use?
Right now we're in about a 14-hour interval, and it lasts for approximately 5 minutes. The indicator, which was going off prior to that, right now is anywhere between 22 to 24 minutes of eruption time. Look, they got soaked. Now we stand there. There's a lot of water on the boardwalk. I told you guys would get drenched, right? Okay, we're just going to...
Yellowstone in northwest Wyoming, land of geysers, mountains, and lakes, is also sitting atop a super volcano. And it just took what scientists describe as a deep breath, causing miles of ground to rise dramatically. So what does this mean? Well, joining us right now is Michio Kaku. He is a physics professor at the City University of New York and the author of the upcoming book, Physics of the Future. Thanks so much for joining us.
Glad to be on.
So the last time this happened was 640,000 years ago. We're due?
We are due. Forget Yogi Bear. Okay, forget Old Faithful. It's sitting on top of a sleeping giant. Now, if you're sleeping next to an 800-pound gorilla, you monitor every burp, every snore of this gigantic gorilla, because when it blows, it could destroy the United States as we know it.
This is a pretty scary prospect. I want to just show people what we're talking about here when we talk about this super volcano, and we have a little thing to show you, a map with some of the details. So that's where it is. It's beneath Yellowstone. It's been there, as we know. I guess this has erupted 3 times in 2.1 million years. But what they're worried about is the fact that they say that the ground has started to swell in levels that they have not seen before, 10 inches in some places in the past year. What does that tell us?
It tells us that there is activity in this supervolcano, which erupts roughly every 600 million years. And the last eruption was 640 million years ago.
Oh, 640 million or 1,000?
1,000 years
Okay,
ago, I'm
okay.
sorry, you're right.
Because then we had some more time.
Then we have some more time, right. But that's what's making us very nervous, because the cycle time corresponds to the present-day era. So every single burp, murmur of this gigantic potential supervolcano, including the rise of the sea level, has to be watched very carefully.
All right, so when we talk about this, and we have pictures pictures of Mount St. Helen erupting back in 1980. Let's just show this right now. You say that an explosion with this supervolcano under Yellowstone, and there we're seeing the Mount St. Helens, would be 1,000 times bigger than this. What type of damage are we talking about here?
We're talking about immediate damage out to 100 miles from the site. That is total devastation, basically wiping out everything in sight. However, the real damage goes out to 500 miles if you include volcanic ash, poisonous gases, death of wildlife and vegetation, and that's a ring about 1,000 miles across. That's the heartline of America.
It would pretty much wipe out Earth as we know it?
It would wipe out the United States as we know it. And again, we don't want to panic anybody. It could happen tomorrow, or it could happen 100,000 years from now. It's black magic trying to predict exactly when it's going to blow, but we do know one thing. One day, it will blow.
And you say that something on this scale is what wiped out the dinosaurs.
65 million years ago, another supervolcano coincided with this meteor that hit Mexico, and we think it was a double whammy that knocked out the dinosaurs. So it's something that we take very seriously, but again, the cycle time is measured on the scale of hundreds of thousands of years.
Would there be anything we could do to prepare or to get people out? I mean, how much of a warning might we get with this eruption?
All you can do is run. You don't get much warning. What happened is the ground starts to rise, more and more earthquakes take place, more ash and volcanic gases start to be unleashed. That's about the only warning we get, because we do not have a good way to predict volcanic eruptions.
Are we getting a better way to do it, or are we just at the mercy of Mother Nature?
We're still clueless. We're still monitoring it very carefully, looking for the warning signs. That's why this sudden rise in the Earth, even though it's not immediately dangerous, is being looked at very carefully, because we have no experience with supervolcanoes. We've seen Mount St. Helens. We've seen Krakatoa, but a supervolcano erupting in our lifetime, we have no understanding of the scope of that thing. We just see the evidence of previous eruptions.
It's amazing. So you say it could be tomorrow, it could be in 100,000 years, but it's under there.
It's there, and it will happen. At one point, it will destroy North America as we know it.
Well, it got dark all of a sudden. Ladies and gentlemen, welcome to the final talk in the geology lecture series this year. I know it's only been 3, but I'm looking forward to a third very exciting, eventful, and essentially hazardous talk tonight. Essentially, it's been the hazard year between earthquakes and volcanoes, and I guess in some respects it goes along with the things that have been happening out there in the real world as well. In the event that as you came in, you didn't sign one of these sheets, if you could take a moment on your way out later this evening to go ahead and sign in. We do like your birthday. Hilda, haven't I sent you a birthday card just because you signed in? Thank you. So if you sign in, I pick one person every year and I send them a birthday card. So please do it. The reason they go for the birthday is essentially when they're pulling people's names out and showing that you were here, it gives us credit for it. It also helps me that if we put in for some of the geology speaker series folks, a lot of times they want 200, 250 people, and so if we can prove that we've actually done that, it helps get more people here as well. I'd like to just take a moment to thank our sponsors as well as our crew up there, who are also a little expanded the last couple times doing a live web stream feed, which I appreciate, and hopefully some folks out there appreciate as well. The college obviously provides the space and also provides the tech. Foundation is also a supporter. Oregon Resource Corporation is a financial supporter, and a special grant this year, the Dorothy Stout grant, was provided to me to help support the talks this year through the National Association of Geoscience Teachers. If you haven't yet, one of the ways that you can keep track of who's coming next year, starting hopefully in the fall, which is usually the difficult term, is if you go to the college's website, you can find it under the geology department. There's a section for the geological lecture series. You'll also hopefully probably be able to find a YouTube link for this, and also Kathy Cashman's talk if you missed it on Mount St. Helens. All of that said, it's my great pleasure to introduce to you this evening Dr. Jake Lowenstern. And Jake is the scientist in charge at Yellowstone. And so over the course of time, he started on the East Coast, much like someone else that I know, went to school as an undergrad at Dartmouth, and went on to Stanford. He's been at USGS for a number of years now, including acting as the scientist in charge, actually only the second scientist in charge at Yellowstone. Correct? Yeah, and so is a pretty interesting place that I'm sure, how many of you have been to Yellowstone? Fantastic. How many of you are here because you've either been to Yellowstone or think maybe that would be a good place to go? Okay, great. So it's my pleasure to introduce to you this evening, without further ado, Jake Lowenstern.
Observatory. And to people in Yellowstone, there's a big difference. It's a partnership between the U.S. Geological Survey, the University of Utah, who actually does most of the instrumentation. They put in the seismic network, the GPS network, some of the things that I'll be talking about during the talk. And then, of course, Yellowstone National Park itself. There's a couple geologists who work in their geology program, and we work closely with them. I actually work out of Menlo Park, California, the other Bay Area, and do my job from there, although I travel to Yellowstone at least 3, 4, 5 times a year. I'm usually there for at least a month, sometimes as much as 2 months in a given year. So that pretty much sums that up. Those of you who don't know, Yellowstone is sitting here in the northwest corner of the state of Wyoming, about maybe 800-900 miles to the east of where we sit tonight. Yellowstone is many things to many people. To some, it is spectacular scenery. To others, it is great fly fishing. Many love the geothermal features. Indeed, it is a unique global resource for geothermal activity. Others are all consumed by what we call the charismatic megafauna, of which bison and wolves are included. And then to a growing number of people, it's all about the supervolcano. This is a promo from a movie that was made a few years ago, BBC Discovery. And it's over maybe the last 10 years, people have gotten kind of interested in this whole aspect of Yellowstone being a volcanic system, and sometimes they kind of go a little bit overboard. This is some of the most crazy journalism comes out of the UK, and I think they just love to hype how all those dumb Americans are about to lose their cookies. But we won't go into this in general, but it's quite entertaining. So over the next few slides, I'm going to give a little bit of background on how we got to where we are, and then I'll get more into the actual geology. And we actually don't know that much about what the Native Americans thought about Yellowstone. Obviously, it was a special place. There's plenty of evidence they went there, but we have no written record of exactly how they felt about it. The first written record that we have comes from trappers such as Jim Bridger, who talked about rivers that raced downhill so fast that they heated up. And there was a lot of a hyperbole associated with the place until finally the fledgling U.S. Geological Survey, for which I now work, sent Ferdinand Hayden out to look at the 45th parallel, and he came out and with his group was able to make these observations, which show that he pretty much understood that Yellowstone was a big volcanic system. He talks about volcanic activity as that of any portion of the globe. It might be called one vast crater made up of thousands of smaller vents and fissures out of which the fluid interior of the earth, fragments of rock, and volcanic dust were poured in unlimited quantities. And talking about how the springs and geysers are the closing stage of this wonderful period of volcanic action. So he and his colleagues rightly understood that Yellowstone was a volcanic place. I don't think they quite appreciated that it was still really living, although they did know, and they indeed witnessed and felt many earthquakes while they were there. And this is written by one of the group members, Albert Peel, how they were woken up by an earthquake, and there were several of them over the evening, and trees were shaken. And indeed, we still witness these earthquakes today, and I'll be talking about some as we go through the talk. One of the first superintendents at Yellowstone was Philotilus Norris, and he was one of the first to describe explosions out of the geyser system, out of the hydrothermal system, or what we call hydrothermal explosions. He had this great quote talking about the pool being considerably enlarged, its immediate borders swept entirely clear of all movable rock, enough of which had been hurled or forced back to form a ridge from knee to breast high at a distance of from 20 to 50 feet from the ragged edge of the yawning chasm. Love that. And it wasn't really until the 1960s that people started to understand the nature of some of the largest volcanic eruptions that we get on the planet. A man named Robert L. Smith, who worked for the USGS, had been mapping out what were called tuffs that were found all over the western U.S. And he recognized that these fragmental, welded, glassy rocks were formed by incredibly explosive volcanic eruptions that would cover thousands of square kilometers in some cases with hot, dense clouds of ash that then form welded sheets. Bob Christensen, working in the 1960s for the USGS at Yellowstone, realized that there was not one, but actually several enormous eruptions that had happened at Yellowstone, the most recent of which was about 640,000 years ago. And so Christensen is really the one who opened our understanding of really all the details of the Yellowstone geologic story. Most of that work was done in the 60s and 70s, and he retired. In fact, he was the first scientist in charge of the Yellowstone Volcano Observatory. The observatory was started in 2001, and he retired in 2002, which is when I took over that job. And here's one figure from his professional paper on Yellowstone, where he shows this green unit, which is the Lava Creek Tuff, which is, again, this very highly explosive deposit that's very thick in all the regions shown in green here. Ash, as we'll talk about later, would have gone much further away from Yellowstone at the time. And this purple unit and this blue unit represent earlier ash flow tuffs or pyroclastic flows that came out of Yellowstone. It was in the 1970s that people realized that the lake bed, the Yellowstone Lake, had been shifting over time to some degree. The southern edges of the lake had been getting flooded over time. The water was getting deeper. And so people realized that maybe something strange was going on. And Bob Smith, who's still at the University of Utah and is the coordinating scientist of YVO for Utah, started working with the USGS folks back in the early 70s. And what they did is they went over the roads of Yellowstone and did traditional surveying, and they compared the elevation of the roads to a survey that was taken in the early 1920s. And they found that in some cases there was about 700 millimeters, or almost 3/4 of a meter, a couple feet of uplift in the center of the Yellowstone caldera, and then smaller and smaller amounts. So these are essentially contours of elevation rise that occurred between 1920 and about 1975. So about 2 feet, the entire caldera had moved up over that time period, and that had caused essentially the north edge of Yellowstone Lake to rise, and the water then moves out towards the south. So that sort of sets the stage of how we began to realize that Yellowstone really was an active geologic place. And today I'm going to talk more specifically in the next few minutes about some of the hazards that exist at Yellowstone, what the relative probabilities of those different hazards are. We'll talk about volcanic eruptions, earthquakes, and steam explosions or hydrothermal explosions. Then we'll go and look a little bit at the big picture of why is this happening at Yellowstone, and what does it look like underneath the ground at Yellowstone. And then I'm going to focus in the last part of the talk on sort of what's been going on in the past 10 years at Yellowstone, what kind of things have we been noticing, and what do we think that it all means. And after that, we can handle any questions that you might have. So in the next series of slides, I'm going to have down here, we'll have this sort of bouncing blue ball that's going to move from low-frequency events to high-frequency events, things that don't happen very often but are often big events, to things that happen quite frequently and in general are smaller in nature. And that's typically the way earthquakes and volcanic eruptions and floods and major storms and everything else in Earth science works, is that big things don't happen that often, little things tend to happen a lot. In this case, we're going to talk about caldera-forming eruptions. And I'll explain caldera a little bit in a moment, but these are enormous eruptions that are so large that essentially the ground surface can no longer support what's beneath the ground can no longer support the ground, and you get a huge crater or subsidence feature that forms because you've taken so much magma or molten rock out and you've spread it out all over the countryside. In the case here, the eruption 640,000 years ago formed deposits that can be found in South Texas, for example. And certainly ash would have gone even further than that, although we don't necessarily have any evidence for that at this point. The 2.1 million year old eruption, which was even larger, this is the limit of where we found deposits from that one. And there was a third eruption about 1.3 million years ago. So 3 very, very large eruptions coming out of Yellowstone. And these are some of the largest eruptions that we know of on the planet. There are other similar ones. There was one 74,000 years ago in Indonesia called the Toba eruption. And so they don't only happen at Yellowstone. The largest one that we know about, single eruption, actually happened in southwestern Colorado in the San Juan Mountains, and that was about 27 million years ago. So these are big eruptions. Yellowstone has some of them, and if they were to happen again, would be a big deal. They'd be a big deal if they happen at Yellowstone. They'd be a big deal if they happen anywhere else on the planet, because as we've seen over the last 2 weeks, even a little bit of ash into the atmosphere can cause a lot of havoc. So we don't actually expect necessarily that there will be another one of these coming out of Yellowstone, but if you just had to average these 3, they might happen every 730,000 years. Doesn't have to happen again, and I just have this thing here on the order of hundreds of thousands of years is how often big eruptions occur. And that would actually be globally. This is just a digital elevation model of northwestern Wyoming. This would be the Teton Mountains right here, and the Gallatin Mountains and the Beartooths are over here. You can see this is steep Rocky Mountain terrain over here and down in here. Interestingly, there's nothing really here in the middle. It seems like the whole terrain is flattened out. This is where the Yellowstone caldera is. This is the Snake River Plain, where there have been eruptions in the past. Essentially, all of the mountains that existed in this region have been swallowed up during enormous eruptions and then covered over by later volcanic debris. And so we've this big volcanic activity in this part of the country has removed some of the Rocky Mountains. So this is the caldera that formed 640,000 years ago. The park boundary is right here. It's about 60 miles by 60 miles, or 100 kilometers by 100 kilometers. Here's the state boundaries. The red lines you'll see in a bunch of these slides represent the roads that go to the park. And this purple outline, again, is the Yellowstone caldera. So in 640,000 years ago, about 250 cubic miles of material was erupted out of Yellowstone in one, perhaps 2-week-long event. Sent stuff out. That's a lot of material to take out of the ground, and as a result, this entire area in here foundered, fell into the ground. Since that time, all of these units, geologic units, have come out. These are all large rhyolite lava flows. So they're the same. Rhyolite is a kind of magma that can come out in very stiff, thick obsidian flows, lava flows, or it can form a very explosive eruptions, such as the ones that formed the Lava Creek Tuff and we talked about earlier. So it's a material called rhyolite. It's usually produced in the crust. It's high in silica content, SiO2, the same stuff that quartz is made of, but it's a little more, it's also got other things in it. So the rhyolites have come out since the last big eruption. They filled in the caldera, so when you go to Yellowstone today, you don't see a big hole in the ground. Instead, you see a hole in the ground that was filled in by continuous volcanic activity that continued until about 70,000 years ago. And if you go to the Grand Canyon of the Yellowstone, you'll see one of these older rhyolitic lava flows. This is the Tuff of Sulphur Creek, and it's found in the Grand Canyon there. And this one's about 500,000 years old. Then we also have these yellow units, and these are called basalts. Basalt is the kind of magma that's typically formed down in the mantle of the Earth, maybe 40, 50 miles beneath the surface. It's what happens when we melt the mantle. So those materials come up and they erupt on the periphery, and they're also found in the Snake River Plain to the southwest. They don't typically form, as you'll notice, here in the caldera itself. So that's one of the pieces of evidence that people used to realize that this was still an active system, and there still was magma beneath the ground, because the rock beneath Yellowstone is molten, and it's made of this lighter, less dense rhyolitic material. And when the basalts come from the mantle, they come up into the crust, and they can't get through this lighter material. The lighter material is partly molten, so you can't crack it. So the dense, deep mantle materials pond and supply heat to the Yellowstone caldera. And outside, where the rock is, where there isn't the magma, that's where the basalt can reach and get out. So these are all these yellow units in this case are young basaltic lava flows that have erupted in the last 600,000 years as well. And here's an example of one up at the Sheep Eater Cliffs, which is in this yellow area right here, finding nice columnar jointed basalts. So our little ball moves over here. These eruptions may occur on the order of every 10 or 20,000 years. Each one of these red dots represents a vent that came out during one of these rhyolitic lava flows over the last 600,000 years. When you include the basalts, there have actually been about 80 eruptions at Yellowstone since the caldera forming eruption. So there's been a lot of activity, but the last one was 70,000 years ago. So the Yellowstone, even though things are going on there today, it hasn't experienced a volcanic eruption in a very, very long time. And it's not that likely that it will do so in the near future. In this case, this is the most recent lava flow, the one that's 70,000 years old, and it forms what's called the Pitchstone Plateau, for those of you who are familiar with the geology of the area. In this particular case, this lava flow is about the size of Washington, D.C., so a pretty big area. And it's about 300 feet thick or so. We also have large hydrothermal explosions, and these have happened much more recently in the geologic past. So this is a lake. It's called Indian Pond. It's about 400 meters or yards across, maybe a little over 1,000 feet across. Here's the road that's coming by outside nearby, and Yellowstone Lake sits right out here. So this is about 4,500 years old. So we're getting post-glacial. After the glaciers left, we have a number of these explosions. Clearly, if you were anywhere near this when it happened, there would be a rain of debris that you would need to avoid, but the debris probably doesn't leave maybe a 5 or 10 mile radius from right here when these things form. Mary Bay, which is right adjacent here outside, is about 3 kilometers or a mile, about 2 miles in diameter, and it was formed by one giant explosion about 15,000 years ago. So there's a lot of these around Yellowstone Lake, and they occur maybe on the order of every 1,000 years or so. So we're getting into the kind of event that actually does happen often enough that you kind of really need to be on the lookout for it. And here are all of these little stars on this map represent hydrothermal explosions that have occurred in the last 15,000 years and are ones that are larger than about 1,000 feet across. And in this case, all of these lines right here represent faults. So here we have the Yellowstone caldera, and these are active faults, so areas that earthquakes can occur on, areas where movement of the crust causes separation and movement of the rocks. These are faults associated with the Tetons. This is out towards Hebgen Lake. And I'll talk about that in a minute. So yes, so here we have all the faults in the general area. Here are where we have the earthquakes. And this is just a subset of the earthquakes over the past 20 years. We typically get somewhere between about 1,000 and 3,000 small earthquakes per year in Yellowstone. So something like this would be kind of typical, actually, for a year at Yellowstone. you'll see many of them are up in this area right here, which extends over to the site of a really large earthquake that happened in 1959 at Hebgen Lake. And I'll talk about that in a moment. And then we also have a few down into the Tetons, some beneath Yellowstone Lake, others near various geyser basins found around Yellowstone, and some associated with areas that are called the resurgent domes that I'll talk about a little bit more later on. So we have big earthquakes as well, large earthquakes and landslides. The last really huge earthquake was in 1959. It was again at Hebgen Lake. Here's a picture that Bob Smith took, or actually I think this is of him back in 1959. It says the fault offset is 3 geology students high, so a crack grew in the ground that was, literally almost 20 feet in height at that particular time. When you get these big earthquakes, they cause changes of the geothermal system, so you see changes in geyser activity, and often we'll notice that the hydrothermal activity in Yellowstone and earthquakes are fairly closely linked. So these big earthquakes might happen on the order of every 100 years or so. The last one was about 50 years ago now was the 1959 earthquake. And here are some pictures of that event. A lot of damage to the roads nearby the park. Some houses slid into the lake, lots of landslides. And in addition, part of a mountain collapsed that created a new lake called Quake Lake and buried about 15 people who were camping in a campsite at the time. So there were a number of deaths associated with this earthquake, and it was a really traumatic event for everybody who lives in that area, and they still talk about it today. And the most common hazard at Yellowstone, we get on the order of every few years, are still hydrothermal explosions, but in this case we're really looking at small hydrothermal explosions. So the geyser system is a column of boiling water, okay? It's boiling at the surface, and as you go further and further down into the crust, it gets hotter and hotter and hotter, because the boiling temperature of water gets hotter and hotter and hotter, and you have more pressure as you move down, so it just stays at the boiling point. So whereas at the surface it's boiling, in this case, at about 200 degrees Fahrenheit, it's boiling at 350 degrees Fahrenheit as you move further and further down. And so we have a column of boiling water, and if, just as in a pressure cooker, if you release the pressure by a big earthquake or by a landslide, you'll get the deeper, more pressurized, hotter water to all of a sudden come to a lower pressure, at which point it explodes catastrophically. And so these are what's causing these enormous hydrothermal explosions that we talked about along Yellowstone Lake, and they're causing these smaller ones that are found all over the park. This one is a place called Black Opal Pool. It formed in 1932. There have been scores of these hydrothermal explosions since the park was first founded in 1872. We see them in pretty much every geyser basin in the park, and we also know that occasionally they can be triggered by earthquakes. Our estimate actually is that there's about one of these small events every 2 years. And we've seen some of them too. In this particular case, this is the Mush Pots, which is a backcountry thermal area that people noticed from a fire lookout that something strange was going on in the summer of 2008. We actually had a field trip that was taking place in a place very close to that Black Opal Pool that I showed in the previous slide. And the geologists were standing around talking about hydrothermal explosions, and that happened. Nobody was actually hurt. None of the rocks actually made it over to the boardwalk, but it does keep you on your toes. So this is an area in the Biscuit Basin, and if you go there on your next trip to Yellowstone, you stand a fair chance of seeing something like that happen. So there's a continuum between normal geyser activity, and these things get clogged up sometimes, and pressure builds up, and you get small hydrothermal explosions, and occasionally perhaps an earthquake or some other event triggers the larger hydrothermal explosions. And we ultimately don't know exactly what triggers them. We just know they happen. Okay, so what's going on? Why is Yellowstone even there? It's certainly not in the Cascades. We have all of these volcanoes that are in nice, beautiful lines around subduction zones, but Yellowstone's all sitting there in the mid-continent. What's going on? Well, Yellowstone is what we call a hot spot, and it's part of a system that has been active for about 16.5 million years. It started about 16 million years ago in northern Nevada, in this area right here. And if you'll see here, we've drawn pictures. This is work by Lisa Morgan and a guy named Ken Pierce, who found and tracked the different large areas of volcanic systems and found that they got progressively younger as they moved towards Yellowstone. And so you see a bunch of extinct volcanoes out here in southern Idaho, and then finally you get over to the very youngest activity, which is where Yellowstone is today. Well, it turns out that the North American plate is actually moving gradually towards the southwest, and apparently over what we consider a hot spot, or and some people imagine it to be a plume of hot material that's coming off of the core of the Earth through the mantle and is rising from very, very deep, perhaps even thousands of kilometers beneath the surface up to the surface. This is one image that's been taken with seismic tomography. They're using seismic waves, looking at that you notice with seismometers, and they're trying to do tomography much like you would do a CAT scan or an MRI. And in this case, here's Yellowstone at the surface, and they can trace something, a change in the speed at which earthquake waves move, all the way down to about 700 kilometers or 400 miles or so beneath the surface of the Earth. And it actually appears that this body is kind of dipping towards the north and west. All we really know is that we can pick out some sort of an anomaly. It's probably slightly molten material, and that's pretty much as good as we can do right now. So it appears that this is a long-living system of melting that's going on in the deep mantle. The crust is moving over this spot, and so if you had the hot spot here, you have a crust moving over it, you'll create a volcanic system at my fingers, later on, right in the middle of my hand. If the hand keeps moving, it'll be back at my wrist. And so that's why we get a progression over time of younger volcanic systems towards the northeast. It's a little bit more complicated than that. There's a lot of earth scientists who argue about exactly how it works and whether there are multiple plumes down there. But that's sort of the simplistic way to think about it, that in detail may only sort of partially reflect the truth. And that's something that we're constantly working at to understand better. So here you're looking at the very enormous magma, this enormous anomaly all the way down. And now the next slide shows you what's right beneath the surface at Yellowstone in the upper 5 miles or so. This is kilometers here. And this is another tomographic image done with a slightly different technique by Bob Smith's group and Stefan Husin back at the University of Utah. And in this case, here's the caldera. And these are what we call the resurgent domes up at the surface. And these are the areas where we see the most uplift of the caldera, like they found with the surveying. And in this case, they think they can track those uplift areas down to areas of molten rock or partially molten rock that are on the order of 6 miles beneath the surface, and seem to be two sort of lobes that have risen from probably a more melted area further down. So this is kind of our conception of what's going on. Again, these would be the rhyolitic material and crystallized rhyolite sitting beneath the surface. And this is what it might look like in cross-section when you're looking beneath one of these domes. You'd find that at the surface, here you are, you've got your geysers. Earthquakes are plotted here as little red dots. You'll only have the earthquakes occurring near the surface because that's where rock is cold enough to actually break. Then down below, you start getting into this rhyolitic magma, which is partially crystalline and partially molten. And then it's all being driven by this basalt, this material that's rising off the deep hot spot, coming into the crust 20 miles or so, is melting the crust, is crystallizing as it cools when it reaches the crust, and that's creating new melts that rise as they're buoyant, and they rise and they form this silicic magma reservoir, this rhyolite reservoir that's closer to the surface. And then above that, that's where all the hot water is. We've got rainwater, it's pushing lots of water down in. We have this high mountain area. The water sits above the magma, and it gets heated by all of this hot material, this molten rock that's sitting only a few miles beneath the surface. And that's creating this hot water system that is boiling at many depths and thus creates the amazing features that we see at Yellowstone, the geysers, the hot springs, the mud pots. Just a little bit more here on some of the hydrothermal features that you see at Yellowstone. Most people just kind of think of them all as hot water, but there's actually quite a bit of diversity as you move around the park. By the way, in this particular slide, all of the black areas represent different thermal areas. So it's not as if everywhere in Yellowstone there are hot springs coming out of the ground. It's really only about 3% of the park is thermal, in that there are thermal features at the surface. Although as you move down, probably you get hot water in many, many other areas that just doesn't get to the surface. So here's an area right here. This is Mammoth Hot Springs. Some of you may have been there. Travertine terraces. This is calcium carbonate, same stuff that makes limestone. It's found at the north end of the park. This is one of the largest active limestone or travertine terraces in the world. And it's very amazing place, but it's also very unusual for Yellowstone. Most of the hot springs and the geysers are not coming out of a limestone or a calcium carbonate terrain. This is really the main area of the park, and it's a colder water that tends to form these sorts of deposits. Water that never gets really up to the boiling temperature of water at sea level. So it's water that's only about 80, 90 degrees centigrade. Then we have areas like the Firehole River basins. In this case, we're at the Midway Geyser Basin. The Lower Geyser Basin is here. Old Faithful hangs out here at the Upper Geyser Basin. This is the heart of Yellowstone geyser country. This is the Grand Prismatic Pool, a very famous pool. In this case, here's the trail, the boardwalk that goes right by it. Different thermophile bacteria or archaea live surrounding the pool, and their different types of thermophiles have different colors, and so they form the different colors that you see. These waters are not saturated with calcium carbonate. They're saturated with silica, SiO2, and it's in an amorphous form, and when the waters are hot and they cool down and they flow away, they leave this silica in terraces that surround the area. In some cases, the silica is coming out in the spraying of the geysers, and it forms things like Grotto Geyser here, which again is made entirely of amorphous silicon dioxide. The same thing that quartz is crystallized silicon dioxide, and this is amorphous silicon dioxide. So this is the material, and these are neutral waters. They're loaded with chlorine and sodium, and they're saturated with silica. The other kind of hot water that you find at Yellowstone is found in places on the periphery, such as here, and this is on the caldera margin. It's a place called Smoke Jumper Hot Springs. And these most people don't know about because even though they're really, really common, they're really quite ugly, and they're acid, typically. So if people sort of went and started putting their hands in, they'd find that their hand would be a little bit unhappy later in the day. Often if you sit on the soils here, you'll notice that you start getting holes in your pants. And so these are what we call acid sulfate features, and they typically have no flow out of them. So there's very few streams that actually go very far that have significant amounts of these waters, and I'll tell you why that is in a moment. But most of the waters that are coming out are the ones that we already saw. The ones that are a large volume are these chloride-rich neutral springs. So the basic idea is you have this magma down below, and it's bringing all sorts of hot heat that's rising up, and you also have hydrogen sulfide that's coming into the system. It goes into the hydrothermal system. So you have heat and materials that are coming up. And then in the low elevations, along the river basins, you get these neutral waters, and you have boiling that's happening in the hydrothermal system, and that's sending steam and gas up to the high elevations, and this is where the H2S that's coming out in the gas is getting oxidized and turns into sulfuric acid. And so you get, in these high elevations, you tend to get the acid waters. There's very little flow involved because it's mostly just steam that's condensing in the subsurface and creating the acid features at the high elevations, and you're getting the geysers at the low elevations. Okay, so the last section of the talk is to talk about what's been going on recently at Yellowstone. And I'm going to go over a number of big events. One was the Denali earthquake, some disturbances and uplift that happened at Norris, Geyser Basin, and then some swarms, earthquake swarms that have happened over the last couple of years. The first thing, I actually started this job. I'm not a seismologist. I'm mostly I study the origin of rocks, and I've studied a lot about hydrothermal systems in my career. I started as the scientist in charge of Yellowstone Volcano Observatory on, I think it was Monday, November 4th of 2002. And on November 3rd, there was a big earthquake in Alaska. And it was a magnitude 7.9 along the Denali Fault. And the earthquake waves that moved away from that particular event moved primarily down towards the southeast. In this case, you're seeing the red dots and the red lines represent seismic stations across the central U.S. here in the Rocky Mountain states that had clipped data. And what we mean by that is that the waves that were coming through those stations, even though they were on the order of 1,500 miles away, 2,000 miles away from the source, the earthquakes were shaking the seismometers so much that the seismometers couldn't actually even record the data. And so you just lose the data in that case. And it was noticed that those happened in here, but there was no problem recording the data down here and over on the other side. So everything was sent directly at Yellowstone, and you can see here it's the dynamic stress in bars are about twice atmospheric pressures coming through the ground. And when that happened, it had a large effect on Yellowstone as well as a few other places. So here's the traces of the seismogram when you're at Yellowstone. In this case, you're looking at the frequency. And so the frequency, there's low frequency surface waves that come from a distant earthquake tend to be only really, really low frequency because the high frequencies all get lost. Kind of like when you yell across the room, you can sometimes only get the really low frequency coming through when you're a long ways away. The high frequencies are gone. And so what happens here is when the earthquake wave came into Yellowstone, and this is time down on this axis and frequency here, all of a sudden you started getting local earthquakes, high-frequency earthquakes. And each sort of red line here, and they're all merging together, represents a different earthquake that was happening at Yellowstone. So all of these were going on over the few hours after an earthquake came in right here. This is the initial wave, and the surface waves come in, and it just set off Yellowstone. It's like the system was pressurized, and the waves came in just at the right angle, and the folks in Utah were busy locating earthquakes for the next 3 days. There were about 500 earthquakes that occurred over a 3 or 4 day period in Yellowstone, all over the park, not just in one area. There's some here beneath Yellowstone Lake, some out here in the geyser basins, some out here near Hebgen Lake, but all over the place, and most of them occurred within the first few hours of this, the passing wave. So this is something that was very interesting. In 1993, people believed that this couldn't even happen. You know, people, if you'd asked if a distant earthquake could trigger earthquakes somewhere else, the scientists all would have said, impossible, doesn't happen. And then there was an earthquake in Southern California that clearly triggered things all over. And this then happened 10 years later, and this is probably the best documented example that exists of a distant earthquake triggering all sorts of activity, and it generally happens in these hydrothermal areas where the boiling groundwater just really is pressurizing the system, and small changes can kind of set it off. In this case, nothing bad happened. There were a bunch of small earthquakes. Nobody got hurt, but it really shows you how living this system is and how sensitive it can be to things going on all around. Now, this is a map showing you uplift in the Yellowstone region, and this is a map made with a technique called interferometric synthetic aperture radar. It's a radar technique taken by a satellite in space. And the satellite, in this case, passed over Yellowstone at 2 different times. You're looking at a satellite, actually you're looking at several images that have been merged, but you're looking at the difference between when the satellite came through in 1996 compared, this image is a 2-year 96 to 98, and the bottom of the image got cut off. But it's a 2-year period, and it's showing the difference in elevation of Yellowstone in those 2 years. How much closer to the satellite Yellowstone got. And so this is a contour, and in this case you're at the north end of the Yellowstone caldera, and this would be the bullseye, and in this case you'd have about 5 inches of uplift over that 2-year period. And then as you move towards the edge of the bullseye pattern, or the sort of the dartboard pattern, you get to no uplift. So this particular area in the park started moving up, and it happened for about 7 years. The total uplift was about 5 or 6 inches. So it wasn't a huge amount of uplift, but it happened in this particular area. People didn't really know about it because we didn't really have this technique going until around 2000, 2001. But we noticed that the caldera had been moving up, and in the very end of this period, in around 2003, it was noticed that there was a lot of strange activity going on in the Norris Geyser Basin, which is just north of here. The first thing that happened was that there were some brand new steam vents that occurred that formed in a crack to the north of Norris in March of 2003. And in this case, it was really loud. If you were standing by the road, it sounded kind of like a locomotive was going by, a really loud steam engine. It behaved this way for a matter of months. This is still an active thermal feature today, although it's much, much reduced in volume and activity than it was 8 years ago. All the trees started dying adjacent to the fracture, and so it became quite a messy place actually to walk because everything kind of started dying. The vegetation, it smelled quite sort of like somebody was making distilling trees, and then so that was one of the first things that was noticed. Later that year, in July, the entire back basin of the Norris Geyser Basin started essentially having anomalous behavior, where the soil temperatures increased so that it was essentially the boiling temperature of water in a lot of places, even right adjacent to trails. Some of the geysers completely lost all of their water and just became fumaroles or steam vents with steam actively emitting 24 hours a day. It's just very anomalous behavior. And this is something that has been noticed over the last 50 years, but this is one of the very intense ones. And now we're wondering whether perhaps these disturbances, as they're called, may be linked actually to uplift in the area. Hasn't happened intensively since that particular year. Here's a thermal infrared image looking down the trail. In this case, you're looking at temperature in degrees centigrade. Here's a fumarole in the background, which would be boiling temperature. But here, right in the middle of the trail, you're getting areas that probably would be about 130 degrees Fahrenheit. And so we do get people walking back there bare feet. Obviously, if you stepped off the trail right there, you'd be in danger of burning yourself. So the park closed off this entire area for about 3 months until things just kind of went back to normal. And then the following spring, not very far from this particular area, some bear researchers were walking in the backcountry in March, and they found 5 dead bison that were all right next to each other. They hadn't been attacked by anything. They were just all dead, right along the edge of the Gibbon River. Things like that don't normally happen, and it was decided that probably what was going on is that it was a really, really cold spell. And when you get these inversions at those times, when the air is completely still, it's about minus 30 degrees Fahrenheit, and all of the fumaroles and everything they just go in, and the carbon dioxide and to some degree the H2S just fill in the low areas. And so these bison probably went to bed in the evening, and over that very, very cold, still night, the gases built up, and eventually they died. So that was another kind of interesting thing that happened at this particular time period. We don't really know that that's really linked to the uplift that was going on or even the disturbances, but it was yet another thing going on at Norris that got people excited. Now this is a more recent image, and from putting together images from 2004 to 2009. In this case, this is the area where we had the uplift before. And from 2004 until the present, this area near Norris Geyser Basin has been going down. But this area, which essentially is the entire Yellowstone caldera except for this area at the very north end, this part has been going up. And the maximum uplift is in this area right here. This yellow triangle is a GPS station we have at White Lake, and it went up about 25 centimeters, or about 10 inches. And that occurred over a period of about 6 years. Most of that occurred within the first 3 years. So we're learning new things all the time. This area goes up, then it goes down. When it goes down, this area starts moving up. Back in the 90s, it looks like this area went up for a while before this started going up, and sometimes these two resurgent dome areas go up together. Sometimes it seems maybe they can even act independently, but just this amount of uplift is on the order of several cubic kilometers of new volume that's coming into the system, because it's such an enormous area that even if you're only moving up 10 inches, it really is a sizable amount of volume increase. Most people think that it's probably magma coming in at depth, maybe 10, 12 kilometers depth. But there are a lot of different arguments about other things that might be causing the uplift. Possibly gas pressure or building up down below. Some people think that it's hydrothermal fluids up near the surface, and honestly, we are not entirely sure. This last picture right here, we have these GPS receivers, and you saw in the last picture here are some of the GPS receivers we have around Yellowstone. They are just single monuments. And so this INSAR technique is great for looking at an entire map of how things are moving up and down. But they really don't tell you very much about what's happening on a day-to-day basis. The GPS receivers don't tell you much on a spatial basis, but they're great about telling you exactly what's going on a daily basis. So you get a great time resolution. And in this case, you're looking at the White Lake GPS data, and this would be horizontal motion in these two, X and Y, and this would be the uplift of the station. And in this case, you're looking at an uplift from about minus 50 to about 200, and I mentioned earlier about 25 centimeters, so this is the same thing, 250 millimeters from about 2004 to about 2010. But you'll notice now it appears it stopped. So some people are, and the fact that it stopped is very interesting, because we've had a lot of earthquake swarms lately, and people are wondering if all of the earthquakes that have been going on at Yellowstone may have been breaking things up, allowing some of the gas pressure to be relieved, and causing the caldera to settle back down. And so we'll see over the next few years if that what we see. Are the earthquakes going to stop? Are we going to stop having uplift, and are we going to start moving into a period of down-dropping of the caldera? So a little bit about the seismic network. We have seismic stations all over Yellowstone. They allow us to locate the earthquakes, figure out how big the earthquakes are, how deep they are, and it allows us also to do the studies, the tomographic studies that allow us to look at what's going on beneath the ground in terms of where is the magma located beneath the surface. We're actually about to do a whole series of upgrades. Most of these stations have technology that's around 1975, and we were given through the USGS funding, through the federal stimulus package, to upgrade 10 of these seismic stations so that we now have sort of modern equipment that is much better at looking at volcanic processes, much better at looking at the deep mantle processes, allows us to do a whole lot more, and it also allows us to get the data out of Yellowstone much better so that we're not as subject to power outages and also and other problems of data movement. So we're very excited about that. And it'll allow us to see things like this even better. This is the earthquakes in 2008, and here we have about 2,300 events occurring in slightly over a year. Each one of these little dots represents an earthquake. In this case, the red ones are outlined because this represents a swarm that occurred between about Christmas and about January 10th, 2008 to 2009. This was a kind of a crazy period. The folks at the University of Utah, it was their break. A lot of people were gone. A lot of people were on vacation, and yet some of these earthquakes were felt by the people who were living at Lake. And it's an interesting thing. There's a lot of people who are very excited and interested in Yellowstone, and when something's happening beneath a lake, it's different than when something's happening beneath the ground, because the ground everybody can see, but nobody can see what's going on beneath a lake. And so it caused the internet world to go crazy with thinking about the end of the world at Yellowstone. In reality, there were a lot of events. There were 21 that were greater than a magnitude 3 earthquake, and so there's a potential to actually be felt, although I think only 5 or 6 of them were actually felt. Another interesting thing is that the swarm actually migrated with time. It migrated to the north, and it appears that some of the earthquakes got shallower with time as well. This is what our web accorders look like. So if you go out and you go onto the internet and you click on one of our seismic stations, in this particular case, the Lake Seismic Station, you see each one of these represents a different earthquake every time you get one of these really fast movements up and down. So you can see it was an incredibly busy time in December 27th, and this is at the south end of the lake at the same time. Here, these are color-coded for times. The blue ones are at the beginning of the earthquake. The red ones towards the beginning of the swarm. The red ones are towards the end of the swarm. And this is the largest earthquake. It was almost a magnitude 4. This one was a little bit different in its behavior than some of the others. You see that the later earthquakes are occurring more to the north. The earlier earthquakes are occurring further to the south. The migration was about 1,000 meters per day, but that's kind of difficult to actually calculate. And then these diagrams are little beach ball diagrams that you don't need to really worry about what they are, but they in this case, when you see the white in the middle, it means that the rocks are moving apart from one another. And this is the typical way that rocks in this part of the country, in the basin and range, act, is that the crust is spreading, and so you expect to see a little bit of dilatancy or outward motion. The one different one was this one, which was a slightly explosive source, and this was the deepest and the biggest earthquake. And so it's thought that perhaps this whole thing was triggered by some sort of pulse of fluid that was coming from depth at the south end and was then triggering hydrothermal boiling water fluids that were higher up in the system, and it's an increased pressure from below was causing water that was in fractures to create more little earthquakes and move on. So that's the best that we know at this point in time. People are still working up the data. And then here's the earthquakes that occurred just this January and February on the Madison Plateau out here. In this case, we actually had 2,400 earthquakes. So the last one was about 1,000 earthquakes underneath the lake. This is 2,400 earthquakes over about, well, most of them were in about a 3-week period. You see, in the histogram, most of the earthquakes occurred in the first 5 or 6 days. But even out into April, we've had continuing activity in this general area. And so it's all out here. In this case, there were more earthquakes. It was a bigger swarm. But I guess I would say that we got less interest from the public on this one than the previous one, partly, I think, because it wasn't underneath the lake. This one, some people out in West Yellowstone felt, but in general, not very many of the earthquakes were felt. So what would we see if there really were going to be an eruption at Yellowstone? Well, we would see swarms. With all of the rock to break at Yellowstone, we would expect we would get tens and maybe even hundreds of thousands of earthquakes. And many of these earthquakes would probably be big, magnitude 5, magnitude 6. And so we'd see a whole lot more of what we already see, but way more of it. Also, the ground deformation that we're seeing, we know has been going on for thousands of years at Yellowstone. We see uplifted terraces around the lake. We know that the uplift can be many, many meters in size, and so the kind of uplift that we're seeing right now seems way, way less than what we would expect before an eruption. In general, I would expect that you'd see a few meters of uplift within the year before any kind of eruption might occur. We'd also start seeing more gas emissions coming out. You'd see greater boiling. You'd probably start to see steam explosions, breaking up some of the rock beneath the hydrothermal system. So in general, we believe that you're going to see a lot of precursory activity that's much greater than the kinds of thing that we're typically seeing at Yellowstone now. If you want to learn more, we have a lot of stuff on our website. It's volcanoes.usgs.gov/YVO. You'll see all of the data, the seismic data, the GPS data. We put up the INSAR images. We show the hydrologic data of the river flows and the chemistry of the river. So there's a lot of data. We tend to put together stories and articles for people to learn more about the ongoing processes. And so there's a lot of things to read there. We also have some basic fact sheets and publications that are oriented towards the lay audience, and they would give you more detail on some of the things that I've talked about today, and I encourage you to take a look at them. So that's what I had, and I'm happy to try and answer any questions you might have. Thank you.
So if anybody has any questions, we've got a live mic over there, and I've got one that basically we need you to use the microphone to ask questions just so that folks in the other audience can hear as well. Questions?
August. Pardon?
You're on. Sounds great now.
Okay. I was, one at a time. I was at West Yellowstone in August last year anyway, at the Mammoth Hot Springs. There was virtually no water at all. Is that seasonal, or is that because of earthquakes and things?
Mammoth has been typically, the park geologists will tell you that the basic amount of water flowing through the Mammoth system doesn't change very much, but it's constantly changing where it is. And so you might go to your favorite place where you saw lots and lots of water before, and it will be completely inactive, but a place way over on the other side has a lot of water flowing out of it. people get very disappointed, especially at Mammoth, because unlike the silica tends to look pretty good for a number of years after water is actually flowing on it. But the travertine, it loses all of the biological sort of silkiness and that you get when there are critters growing in mats on the travertine, make it look quite beautiful. And when the water stops flowing, it just turns into gray, sort of dead bone-like material. And so it's really noticeable when the water stops. But typically, the cracks seal up, the water can't get in anymore, it finds another place, and sometimes in its place where people can't even get to it very easily. So you really need to kind of walk over the entire terraces.
Well, that's what my question is. Is Mammoth basically, as far as the water you had a beautiful picture there when it had water. Is that ceased to be at this time?
No, there are parts of Mammoth that are still...
No. Just right there. You know, where you go to the top of the hill and you can look down?
Right.
And you see them down from the bottom of the hill? There was no water.
Right. Well,
is that, what I'm trying to get at, is that year-round, or does it come and go through the year?
Well, there would have been some water in some parts of it.
Well, there are little puddles up at the top, but I mean, when I say puddles, 15 feet and around, 20 feet maybe.
It's not a seasonal thing. Okay. It's more like several years will go by and there's no water in a certain area. But what we do know is that water that comes out at Mammoth goes back underground, and it comes out at a place called Boiling Spring. And there's a weir measuring the amount of water that's coming out. And that water stays the same amount year after year after year. So
it's going somewhere.
It's going somewhere.
Okay. Thank you.
And it should continue to be a beautiful place, but sometimes you get there, it's not so great, sometimes it's better.
Oh, well, it's still pretty. It just didn't look like the pictures.
Yeah. Surely there must be some other questions.
Are the fumes that come out of these vents, are any of them toxic, or is it just they displace the oxygen?
No, they are toxic to some degree, especially, Yellowstone's a windy place. And so for the most part, if you just go out there onto the boardwalk, the amount of toxic fumes you get is going to be very, very low. But if you were to sleep on the ground on a windless night, you'd be sick in the morning. So it's something that if you're just walking through, most of the time it's all going up. But if you were to spend a week camping in the middle of a thermal area, especially some of these acid sulfate thermal areas, you might find yourself getting a little sick at times. It's not great stuff for you to be around all the time. But again, for people just passing through, in any sort of board